Hi, so my research is mainly centred around one volcano in southern Chile called Mocho-Choshuenco. And one of the principal aims of my PhD has been to try and reconstruct the post-glacial explosive history from this volcano, so roughly the last 18,000 years. But unfortunately, this hasn't been quite as easy as we'd hoped, so we've come across quite a lot of problems in doing this, and a few of these problems I'm going to go through in my talk today. So Mocho-Choshuenco is located in the southern volcanic zone in Chile, which is a volcanic arc stretching roughly from Santiago in the north down to Coyhaique, where Volcano Hudson is in the south. So Mocho-Choshuenco is located roughly in the centre. It's not a very well-known volcano, but it sits between two of Chile's most famous volcanoes. We have Villarrica just to the north, which is one of the most active volcanoes in southern Chile, and just off the map here we have Villarrica, which Sebastian talked a bit about yesterday. So in this map here, we have the blue dots represent localities where we've confidently found deposits from Mocho-Choshuenco. So we can see on land we find evidence roughly 60 kilometres to the north, where it's found interbedded with deposits from Villarrica, Quechipien and Lanín, and also to the east, where again it's around 60 kilometres. Unfortunately, to the east, we rarely get anything preserved on land further east than here, because Argentina has very strong winds and topographically you just get nothing really preserved Tephra-wise. So why are we interested in Mocho-Choshuenco volcano? Well, the first reason is volcanic hazards. Some previous work has suggested that we might have at least 3 eruptions with deposits greater than 1 kilometre cubed. Now, this doesn't seem very much in the context of some of the talks we've had over the last few days, but in southern Chile in post-glacial times, these eruptions that have volumes greater than 1 kilometre cubed are actually very rare. So in this figure here, we have the isopachs of all the published data on eruptions where they have volume estimates of roughly 1 kilometre cubed or bigger. And we only have around 15, which isn't very many. And the fact we're getting 3 just from this one volcano starts us thinking, well, could this be quite a hazardous volcano? Secondly, we're interested in testing some regional hypotheses. So one hypothesis that's been put forward in Chile is that maybe after the last glacial maximum, we have a peak in volcanic activity like we see in places like Iceland. But in order to properly address the volcanic hazards and to test these regional hypotheses, we need really detailed, high-resolution explosive stratigraphy where we can quantify and qualify the style, the frequency and extent of these events. Also, as a lot of people said, they're very useful stratigraphic markers. And in this region we have a large number of lakes, and a lot of these have been cored to explore other questions such as the paleoclimate record and the earthquake record. So this area's had some of the largest earthquakes we've ever recorded. So these Tephra units knowing a lot about these Tephra units and being able to chemically fingerprint them has a very useful multidisciplinary approach in this region. So Mocho-Choshuenco, it's a volcanic complex. So as well as activity from within the main caldera, we have around 40 of these minor eruptive centres too, and these are expressed as scoria cones. Now, these are erupting synchronously with the main edifice, which actually adds a lot of complexity when trying to unpick the eruptive history from this volcano. So the problem with them is we might find a scoria deposit that's 1 metre thick, but if it's coming from a cone only half a kilometre away, that's going to give us a completely different idea of the scale of the eruption to if it's coming from the edifice, say 20 kilometres away. But unfortunately, these scoria units are almost virtually impossible to chemically fingerprint from Mocho-Choshuenco. So as I touched on this, there's very little previous work that's been done. We have a handful of master's theses and 1 field report by Serna Camille. And all they really describe is 3 of these large events and 1 historic eruption. So could this be that this volcano just isn't very active in the post-glacial times, or are we really undersampling the eruptive history from this volcano? So all this previous work has almost solely relied on field observations and a handful of whole rock analyses. Now, the whole rock analyses isn't particularly robust, partly because of crystal setting and also because preservation in this region means we get a lot of alteration. So to give you an idea of some of the problems we have in the field for preservation, I've got a few field photographs. So, in this photo here, this is actually a surprisingly good outcrop from Mocho-Choshuenco. And what I wanted to point out is it's very hard to tell between scoria and pumice deposits. So at the base here, we have a very well-sorted orange-weathered pumice deposit. But in between here and here, we've got lots of these well-sorted orange-weathered units. And even when we dig into the outcrop, they're still orange. Even the cores are orange. So we're like in the field, wow, there's quite a lot of these silicic eruptions. But when you finally get back to the lab, you realise that these are all scoria, they're basaltic andesite. And this isn't even a particularly old deposit. They're only between 3,000 and 8,000 years old. So it's quite poor preservation for relatively young deposits. Another problem we have is everything sort of turns to clay as well. So this is actually a large pumiceful deposit, but you can't even really see the original class shape. So making measurements of MP is virtually impossible. And any original distinguishing characteristics this unit may have had in the field is unfortunately long been lost. So when it's just erupted, we'd hope it would have been a lovely white pumiceful deposit, but no more, unfortunately. So this is about 12,000 years old. And then finally, they often become quite nondescript. So we've got lots of units that just sort of weather relatively thin, but they all look very similar. And but this again, it's not very old. We're again about less than 1,000 years. So we've been finding using field observations is a very tricky technique in this region to reconstruct the stratigraphy. This is particularly problematic when we look at the pumiceful deposits. So previous work identified two sort of Plinian-style fall deposits from this volcano, but we actually find there's at least 7, and they all look very similar. They all have sort of this well-sorting, they're orange-weathered in the field, any subunits that are preserved in a few rare outcrops, but it's only in a few rare outcrops, so everything starts to look the same. Unless we are fortunate to have multiple of these units preserved in a single locality, it's very hard to confidently know which unit is forming this deposit. So, because of these problems, we started to do some geochemistry. So the first thing we did was some glass. Okay, so these are just 2 Harker plots. We've got silica on the X, and sodium, potassium, and phosphorus. So the different colours and symbols represent different units. So we've got about 3,000 data points in this figure here. So first thing, there is clearly more units than the previous work suggests. But what we can see is some of these units are fantastic for correlating. We've got these lovely distinct clusters here for this orange unit, and this dark purple unit here has a very unusual sort of phosphorus signature. So we can be quite confident in correlating these deposits based on their glass chemistry. But if we zoom into here for the dacite and the rhyolitic end, we see that, so we've got 3 units here. But actually separating these out is quite tricky. So you could argue the green is slightly more evolved than the red, and the blue seems to be a bit more shifted to the mafic end. But when we start looking at the actual spread of the data, there's quite a lot of overlap. So I would argue you cannot tell between this green and this red unit, especially when you consider the errors. And yet you could argue the blue is different, but that's assuming that we have a sample and we're able to get those 30 data points or more off the sample. Unfortunately for this unit, that's rarely possible. So we've not only found the problem with the glasses being quite similar in composition, so we're not confident in identifying between them, but the glass is rarely what we call ideal for analysis. So what we would love to have is a great glass like this. We can easily get our nice sort of 10 micron patch on there from the probe, but what we end up with normally is glass that's very skeletal, so we're lucky to even find 1 micron patches, which we just can't analyse, or they're just full of microlites. So this is very typical for a lot of the scoria deposits. Or they're just altered, and when this isn't even very old, but all the glass is already sort of eaten away, so we just can't really do glass analyses on these sort of shards. So because of these problems, we decided we need another technique to really do these robust chemical correlations. So we chose iron titanium oxides. So iron titanium oxides are a group of minerals, and the ones we most commonly get in Tephra deposits are ilmenites and magnetites. So these are the titanium-rich end members, and the magnetites are your iron-rich end members. They're fantastic to use. They're really common in Tephra samples, and they're really quick and easy to sort of analyse. You just need a handheld magnet, and they just come straight out of your crushed samples. They're also far less susceptible to alteration than glass. And also, rather nicely, if we get both an ilmenite and a magnetite, so an oxide pair, there's a test we can do which can test for equilibrium to check, did these oxides form in the same melt? Because they equilibrate so rapidly, we'd expect them to equilibrate with the melt. But if the ilmenite and the magnetite composition fails this test, we can therefore say this must be a xenoglyph and go back and check what we analysed, or maybe this the chemistry has been changed by weathering. Also, another thing we can work out from the composition is the temperature and the oxygen fugacity of the magma, which is a useful thing to be able to determine. So what does this data look like? So if we look at the ilmenites on the left and the magnetites on the right, against Fe2O3 and magnesium on the Y, again, same as glass, the different colours and symbols represent different units. Those green, red and blue units we couldn't tell apart previously now have fantastic little clusters. So this seems to be quite a good technique for separating out some of the units, but it doesn't always work. Yes, we can say it works for quite a few units, but if we look at this black unit here and this brown unit, which we might just be able to make out, the composition isn't very distinct, it's quite spread out. So it's not ideal for correlating. Also, we can't always analyse these iron titanium oxides. They're often far too small to even find on the probe. So though it seems to work for some units, we find that it only really works for the more evolved magmas, so the dacites and the rhyolites. And also we tend to find we get this better clustering and better chemistry when we've actually got pairs, so both an ilmenite and a magnetite present. So we see this for most of the elements we analyse. And as I briefly mentioned, we can also work out the oxygen fugacity and the temperature from these oxides, and these also seem to provide a useful tool for correlating. So you can see the different units also seem to have slightly different trends on these two, for these two features. So what do we do once we've done all the correlating? So, sorry, there's a lot in this figure. So this is the stratigraphy that we've been able to determine from Mocho-Choshuenco. These are all just key stratigraphic columns that we found in the field. And the different colours represent different units and how we've been able to correlate between the different units with a combination of our field observations and our chemistry. And so what we find is we've got at least sort of 28 units preserved, and each of these units we interpret as a separate eruptive phase. But of course some of these have subunits as well. So it seems that this volcano is quite a bit more active than we previously thought. We can also make estimates of the volume from these new correlations we've been able to do. So this is the largest known eruption we've been able to find from Mocho-Choshuenco, and it occurred roughly about 12,000 years ago. And so when we draw the isopach, so these blue dots and green dots are where we've actually been able to confirm the deposits and measure thicknesses in the field, we find the volume's about 5 kilometres cubed, which is a decent size. So to put it into a bit of context, the Mount St Helens, we were looking at about 1 kilometre cubed for the total deposit, and then the 91 eruption of Pinatubo was about 10 kilometres cubed. But then these are historic eruptions, and this is very much a minimum estimate of the original eruption size. We can also use these to work out, well, where do we expect this deposit to be a useful marker bed in the surrounding lakes, in these blue areas here. Also, where do we expect to be a useful marker bed around other volcanoes as well? So we can use if we can chemically find this deposit around Gima, well then maybe that can provide us with a useful age constraint in the Gima stratigraphy as well. So when we combine all of this, as well as radiocarbon dates, we can start having a look at the eruptive frequency through time. So on the y-axis, we have the magnitude. So 5 is roughly equal to eruption of about 1 kilometre cubed, and 6 is one which about the Pinatubo size of 10 kilometres cubed. On the x-axis, so starting from present day back in time, we have the calibrated, modelled radiocarbon ages. So the width of the base of these triangles is equal to the 95% confidence range that we think of what we think this eruption occurred. And the areas and the triangles are shaded to roughly the average glass composition as well. So we can start sort of teasing out maybe a few sort of patterns in this. We seem to see that these 3 large pumice eruptions occurred relatively close in time, so between about 12 and 8,000 years ago. And then it seems that it's a bit more active in recent times. There seems to be a few more eruptions, and the composition tends to be a bit more primitive than the earlier events. And there seems to be this sort of unusual break. Now, between about 8,000 years and about 3,000 years, all we get preserved are these sort of minor scoria deposits, which we think probably are just coming from the cones. So is it that we've got a break in activity from the main volcano edifice? Or could all these features just simply be down to preservation, that we're just undersampling the activity from the volcano during this time? So just to conclude, we find that this volcano is a lot more active than we previously thought. We've now been able to probably reproduce the most detailed post-glacial explosive stratigraphy of any volcano currently in southern Chile. We also find evidence of 4 large explosive events. Now this is currently unique in southern Chile. There's a few volcanoes that have 1 or 2 eruptions of this size, and Hudson has got 3, potentially 4, depending what you think about the new one that's just been discovered. But in general, seems to be quite unusual. So is Mocho-Choshuenco unusual to have so many large events? And then finally, we really need a combination of techniques in this region to really form a robust explosive stratigraphy from the volcanoes. And thank you for listening.
Questions?
Yeah, something a little bit different from what we've all been talking about, but looking at your frequency estimates with composition as well of the eruptions, do you think you'll ever go into looking what that's telling you about the evolution of the magmatic system beneath the volcano?
Yeah,
because it seems to me that you've got very large sort of silicic eruptions tailing off into more basaltic or basaltic andesite compositions, only to then switch back to larger sized silicic eruptions. And we see something very similar on some of the super eruptive provinces like the Snake River Plain, where you have huge silicic eruptions followed by, well in that case it's effusive eruptions of basaltic lava, but still over time, even in the rhyolites, you're getting progression towards slightly less evolved compositions and an indication of an increased mafic component. And we see a repeated cycle as well, and that's the sort of thing that's being teased out here, this kind of repeated high volume silicic units and lower basaltic ones. Is that something you're going to look into maybe?
Yeah, that's the plan next.
Oh, that's the plan next.
Okay, so getting the stratigraphy is a very useful tool for us to then be able to explore some other questions, but getting to this stage it's surprisingly time consuming. You think, oh, it's just a few eruptions, but you're unpicking it from all these poorly preserved outcrops, so it can be quite time consuming. But yeah, it'd be very interesting not just to see if it's at this volcano, but if other volcanoes in the region seem to show this similar trend or shift in more mafic composition.
No, it's really nice. It looks like you've got some patterns coming out, and I think it's looking really nice. So, yeah, thank you.
Okay.
Looking at the same slide, it looks like there's a decrease in the magnitude during the mid-Holocene.
Yeah.
But this is also the period that was much drier and when vegetation density was much lower. So do you think this can be a preservation issue in your terrestrial environments?
Yeah, I wonder that, because not just that, the fact that we're not really getting anything for 15,000 years ago, even though the glaciation is going to happen 18,000 years ago. But I guess if we haven't got many trees or soil, we're just not going to preserve it on land. So it'd be very interesting to see if in the lakes we can actually pick up some older events. So yeah, quite interesting.